Today, in this video, we will see derivation of Flexure formula for pure bending. First, consider this rectangle. This rectangle is before bending, and this second figure is after bending. So, this EF is neutral layer, and before bending and after bending, this neutral layer is same. This means this EF is equal to E dash F dash. Neutral layer not change before bending and after bending. This GH layer is at a distance y from neutral layer. This after bending R is radius of curvature of the neutral surface. Theta is angle subtended by the beam at length O. So we will see step by step this derivation. First, this R is radius of curvature of the neutral surface. Theta is angle subtended by the beam length at O. This is angle subtended by the beam length at O. This neutral layer is same before bending and after bending. Therefore, EF is equal to E dash F dash. Since EF is neutral axis. This angle theta is equal to, this angle theta is nothing but the arc upon radius, and arc is this E dash F dash. This angle theta, this angle theta is arc upon radius. Arc is this E dash F dash, and radius is this arc. So angle is equal to arc upon radius. Angle is theta is equal to arc. At neutral axis, arc is E dash F dash upon radius is this R, capital R. Therefore, this E dash F dash is equal to theta into R, and this E dash F dash is equal to EF. See here, EF. So EF is equal to theta R. This is equation 1. Now next, again apply this angle equation to this G dash H dash arc. G dash H dash arc is at a distance y from neutral axis. So again, angle is equal to arc upon radius. Arc is this G dash H dash and radius is, for this G dash H dash arc, radius from point O is capital R plus small y. And angle is theta. This is equation 2. Now next step is strain in GH. Strain in this GH layer. Strain is change in length to the initial length, or change in length upon original length. So right here, change in strain in GH is equal to change in length upon initial length. Change in length, that means final length minus initial length. And for this GH layer, final length is this after bending G dash H dash, and initial length is this GH before bending length. That means after bending length, final length, minus initial length upon initial length or original length. This GH layer final length is G dash H dash minus initial length is original length GH upon initial length is GH. And from 1 and 2, see here, this 1, EF is equal to theta r, and see here, this EF distance, see this EF distance here, this EF distance and this GH distance before bending is same. So here EF is equal to GH also. EF is equal to this before bending GH. Right here GH. GH is equal to EF is equal to theta r. This is equation 1. And this equation 2 is theta is equal to G dash H dash upon R plus Y. That means G dash H dash is equal to theta in bracket R plus Y. This is equation 2. This is equation 2. Put this 1 and 2 in this strain in GH equation. G dash H dash is nothing but the theta in bracket R plus Y minus GH is theta R upon GH is theta R. This is strain in GH. Calculate this strain in GH. theta r plus theta y minus theta r upon theta r. Simple mathematical calculation, theta r upon theta r plus theta y upon theta r minus theta r upon theta r. This theta r upon theta r cancel, this theta r upon theta r cancel. That means, and this theta cancel. Y upon r is strain in GH. Change in length upon original length, strain in GH is y upon r. This strain in GH is y upon r. Put this equation 3. Next, now strain in GH due to tensile force. Strain in GH due to tensile force. For this step, use Hooke's law. Hooke's law is stress is directly proportional to strain. As stress increases, strain also increases. Stress is equal to E into strain. This E is modulus of elasticity or Young's modulus. And from this equation, this strain is stress upon modulus of elasticity or elastic modulus. Put this equation 4. Comparing this equation 3 and 4, this is strain in GH and this is also strain in GH due to tensile force. So comparing equation 3 and 4, y upon r is equal to sigma upon E. Or rearrange this equation, this E this side, E upon r is equal to sigma upon y. This is equation 5. If this E and R constant, that means if this E and R constant, that means this sigma is equal to constant into y. That means this sigma is directly proportional to y. See here, the stress is proportional to the distance from the neutral axis. See, as stress increases, distance from the neutral axis also increases. So at neutral axis, stress is 0. That means y is, when y is 0, stress is also 0. And when this y, distance from neutral axis, increases, the stress also increases. That's why at this neutral axis stress is 0, and when this y goes away from the neutral axis, the stress gradually increases as y increases. That's why this sigma is directly proportional to y comes from this equation 5. The stress is proportional to the distance from neutral axis. Stress as neutral axis is 0, and if distance measures away from the neutral axis, then stress increases. That is meaning of this sigma is directly proportional to y. Now next is consider section of this rectangular part. This is section of this rectangle, and neutral axis is this. At a distance y, consider one small small part delta a. This is at a distance y, and at this gh layer small part delta a. Consider an elemental area delta A at a distance y from neutral axis, and from equation 5, see from this equation 5, the stress sigma on this element is, so right, from equation 5, stress on this element sigma is equal to E upon R into Y. Now force on this element is, force on this element now force on this element for calculating force on this element, use stress formula. Stress is equal to force upon area. Stress is equal to load upon area. Load is this force, and force on this force, that means load. Consider here force is load and this F is load. Stress is equal to load upon area, and load is, that means force on this element is sigma into A, and this area, that means this A is delta A here. We calculate for element, that means delta A, right here delta A. Sigma we get from equation this E upon R into Y. Into delta A. Moment of resistance of this element force about neutral axis, E upon R into Y into delta A about this neutral axis, moment of resistance of this elemental force, that means movement about this neutral axis. What is movement about this neutral axis is, this is force. Consider this is force about this axis, and movement is P into E, that means this force into distance y. So force is this E upon R into Y into delta A, and distance, perpendicular distance to this force is y. That's why write this on next slide. Moment of resistance of this elemental force about neutral axis is this force E upon R into Y into delta A, and multiply by perpendicular distance to this neutral axis is y. That means E upon R y into y square into delta I. That means total movement resisted by the section m dash is given by so this is sorry this is moment of resistance of the elemental force. Only this element, for this element moment of resistance is this E upon R into y square into delta I. Now for total section, for this total section moment, calculate moment of resistance. How to calculate moment of resistance for this total section? We have this small element moment of resistance. Now integrate this small element moment of resistance, we get total moment of total for this total rectangle, we get moment of resistance when we integrate this small element moment of resistance. Okay, so total moment resisted by the section m dash total moment resistance m dash, consider this m dash is integration of elemental this element moment of resistance E by R into y square into delta I. Take this E by R common, we consider E by R constant here, so constant take common E by R, then integration of y square into delta I. This y square into delta I is nothing but the moment of inertia. Moment of inertia is y square into delta I. So see our last moment of inertia video, you get clear concept for this, where I is equal to integration of y square delta I. This is moment of inertia. Therefore m dash is equal to E by R into I. This is equation 6. Now from equilibrium, this m is equal to m dash. This is m E I upon R. So for equilibrium, this is moment of resistance. And for equilibrium, this moment of resistance is equal to moment. So moment is equal to moment of resistance. Why for equilibrium this moment is equal to moment of resistance? Because if if this moment of resistance is less than moment, then section is unsafe. And if this moment of resistance is greater than moment, then section is safe, but it is economical or any other reason. But for equilibrium and for economical section, this moment of resistance is equal to moment. That's why here I write m is equal to m dash. M is moment of moment, bending moment, and m dash is moment of resistance. So this m dash is equal to m. Equation 6 becomes m is equal to, write this equation 6 as m is equal to ei upon r. And from this equation, rearrange this equation, m upon I is equal to E upon R. This is 7. And here from equation 5, see, E upon R is constant, is equal to sigma upon Y. And here m upon I is equal to E upon R. And here also E upon R. So from equation 5 and 7, we get bending formula or flexure formula. F upon I is equal to sigma upon Y is equal to E upon R. So we get bending formula or flexure formula. M upon I is equal to sigma upon Y is equal to E upon R. This I is moment of inertia. Y is distance from neutral axis to GH layer distance. E is modulus of elasticity or Young's modulus. R is radius of curvature. This M is moment of resistance or bending moment, and sigma is stress. So this is bending formula or flexure formula. M is moment, I is moment of inertia, sigma is stress, Y is distance from neutral axis to GH layer distance, Y E is modulus of elasticity or Young's modulus, and Y is R is radius of curvature. So once again see steps for solving this derivation of flexure formula for pure bending. First step is this calculate by using this angle equation. Angle is equal to arc upon radius, theta is equal to E dash F dash upon R. Calculate this arc, E dash F dash is equal to theta into R. and this E dash F dash is EF, and this EF is GH is equal to theta into R. From this arc equation we calculate this EF, GH and E dash F dash. Again calculate this length also, G dash H dash also. G dash H dash we calculate by using same equation, angle is equal to arc upon radius. G dash H dash is equal to theta in bracket R plus Y. Now calculate strain in GH. After calculation of this length EF, GH, E dash F dash, G dash H dash, now calculate strain in EF. Strain in GH. The strain in GH. For calculation of strain in GH, use formula, strain formula, change in length upon initial length. Change in length is final length minus initial length upon initial length. Final length for this GH is after bending this G dash H dash. Initial length is this GH upon initial length is GH. Put this equation 1 and 2 G dash H dash GH here in this equation. G dash H dash is here theta into R plus Y, and GH is theta R. This is theta R, okay, upon theta R. This is strain in GH, Y upon R. Again, strain in GH due to tensile force. Using Hooke's law, stress is directly proportional to stress is equal to modulus of elasticity into strain. Therefore, strain is equal to stress upon modulus of elasticity. This is equation 4. Using equation 3 and 4, Y upon R is equal to sigma upon E. Rearrange this term. E upon R is equal to sigma upon Y. This E upon R constant, sigma is directly proportional to Y. Now section for this neutral axis, calculate stress on this element. Stress on this element is this E upon R into Y, and force on this element is this. By using this stress formula, stress is equal to force upon area. Force on this element is E upon R into Y into delta A. Now moment of resistance of this elemental force about neutral axis is moment. Calculate moment about this neutral axis. Moment is this load into P into E. Load into perpendicular distance. This load is this E upon R into Y. E upon R into Y into delta A into distance is Y. Total moment resisted by the section M dash is given by, integrate this term, we get E upon R Y square into delta A. Y square into delta A is moment of inertia, and for equilibrium condition this M is equal to M dash, and equation 6 becomes M is equal to EI upon R. M upon I is equal to E upon R. From equation 5 and 7 we get this bending formula. M upon I is equal to sigma upon Y is equal to E upon R. M is moment of resistance or moment. I is moment of inertia. Sigma is stress. Y is elemental strip distance from neutral axis. E is modulus of elasticity, and R is radius of curvature. So this is derivation of Flexure formula for pure bending. Steps are important in this derivation, calculation and steps. This angle calculation step is first step. First calculate by using this angle formula, this E of GH distance, G dash H dash distance. Now second step is calculation of by using strain formula. Now this one term is also important, strain due to tensile force. Now comparing this tensile force strain and normal strain in GH. Now again, stress on this element, by using this equation, stress on this element we get E upon R into Y. And force on this element from this equation. Stress is equal to load upon area. Force on this element is stress into area. And stress is E upon R into Y, this previous stress. Again, moment of inertia, that means moment for whole section movement, integrate it. And again, from for equilibrium, M is equal to M dash, M is equal to EI upon R. M upon I is equal to sigma upon Y is equal to E upon R is flexure formula or bending formula. Thank you very much.